Hey, I'm Ozgun. I'm the CTO at Citus Data, and I'm really excited to be here. Today I'm going to talk about a new concept that's unique to Postgres called extensions. PostgreSQL already has 300 extensions available, and I think these extensions can change how we build, use, and think about databases in the future. Before I start, I also had a quick question for you. How many of you have heard of Postgres? A good chunk, almost everyone. And how many of you have heard about the extension APIs? Cool. Yep. Let's get started then with the introduction slides. I'm Ozgun. I'm the CTO at Citus Data. Previously, I worked in the distributed systems engineering team at Amazon.com, and I love Postgres. Our team also loves Postgres. At Citus Data, we focus on scaling up Postgres and making sharding simple. So you can focus on your application and not your database. At Citus, every single engineer on our team shares the same mission, to make it so that you never have to worry about scaling your database again. And how do we do that? We do this by using something that's unique to Postgres, called the extension APIs. And that's the topic of this talk. Today I'll do something different and start this talk with its punchline. If you're going to take away two things from this talk, they are the following. First, Postgres gets many things right. It's open source, it's reliable, and it comes with an advanced feature set. But if you look at all other databases out there, the one thing that's unique about Postgres is its exhaustive extension APIs. Second, these extension APIs are so powerful that they can change how we build and use databases in the future. Okay, and this talk is about those two topics. First, what is a PostgreSQL extension and what's unique about it? Second, why can these extensions change the database landscape? Third, extensions are a new concept. As with any new concept, we face many preconceptions over the years about what relational databases can and can't do. For example, hey, relational databases can't process semi-structured data. Or, wait, SQL doesn't scale. And in this talk, I'll cover 4 example extensions that speak to these preconceptions. Because I'll show you 4 related but separate extensions, one way to think about this talk is as 4 separate lightning talks. This way, if you're super bored during the talk, you just have to wait it out for another 3 minutes or so, and I'll be talking about something completely different. Cool, with that, let's get started. First, what is a Postgres extension? In simplest terms, an extension is a packaged and versioned piece of software that adds functionality to Postgres. At a high level, Postgres' extension framework offers 2 things. One, it defines a framework to build, initialize, and load related objects into Postgres itself. 2, it defines the contract and the APIs where a developer can hook into Postgres database modules with the intent to override, cooperate with, or extend them. And these APIs first became available several years ago. And with each new release, Postgres and the Postgres community has been discussing and adding more extension APIs. Here's a list of database modules you can override or extend in Postgres' latest release. And of course, some of these modules also depend on other ones. For example, if you're writing a new data type, you may need to introduce new operators or new aggregate functions to operate on that data type. Or if you're extending the query planner to execute queries over a distributed system, you probably also need to extend the query executor to operate on that distributed system. So in summary, you can override or change almost all database modules' behaviors in Postgres. This way, you can expand a specific module's behavior while also benefiting from the diverse features built into Postgres over the past 2 decades. Now, a natural follow-up question is, this is interesting, but why think about extending databases? Why are extensions so important? And why spend all this effort in modularizing an already solid database and provide APIs to extend any database subsystem? The reason is that every decade brings new workloads for databases to handle. As a result, we see specialized databases emerge to handle each new workload. And many commercial databases, I think dozens of them actually, already took Postgres over the years, forked from the core project, and then built specialized databases. Of course, when you fork a database, you start diverging from Postgres and its community. Over time, your database becomes a separate entity on its own. The question is, what if you could leverage all the benefits of a vast ecosystem and a vast feature set that comes with Postgres, and also build specialized databases for new workloads? That would be a game changer. Now, I don't take the word game changer lightly. In fact, we've been working on the extension APIs for over 4 years. And during this time, we talked to dozens of database experts and received plenty of critical feedback. Let's frame it that way. And when we stepped back to evaluate this feedback, we found that it fell into 2 camps. One group of database experts asked us, okay, can you really hook into any database module's behavior? With them, we shared the previous slide that I just showed you about the list of database modules, the Postgres documentation, and different bits and pieces that extended Postgres. The second group of experts, who built usually new databases from scratch, had different thoughts. And when we talked to them, we realized that almost everyone in this camp, PostgreSQL, because it's classified as a relational database, as this rigid, unchangeable database that already placed its technical bets. And it can't be further away from the truth. Well, we had these conversations, and then we almost always heard questions on, hey, Postgres extension APIs can't do this, or it can't do this other thing. Relational databases are not meant for this. You can't build a custom database using Postgres. So rather than discussing this idea in the abstract, we asked them, okay, what specifically can't extensions do? Here are 4 specific workloads that we heard over the years, and in fact, the complete list is longer. We also heard questions about graph databases, GPU processing, data auditing, and others. And in fact, most problem domains already had a Postgres extension that was already in the works. For this talk, I picked 4 example workloads that we frequently heard, and that each already had a fairly stable extension. So the most common objection we heard early on was around handling semi-structured or unstructured data. Most people view Postgres as this relational database where you have DBAs, they create heavily normalized schemas. And the NoSQL movement heavily critiqued this formal approach and popularized the term semi-structured data. In fact, both formal and semi-structured data types have their benefits. And over the years, Postgres added new data types to process various forms of semi-structured data. Today, the most popular of these extensions is the JSONB data type. And let's look at a simple toy example. In this example, we're tracking book entries. And in here, let's see if I can use this. Each book has a unique identifier, and there's a big JSONB column in there. And for all other attributes other than a unique identifier, you just create this data column and then store your data as a JSONB within the JSONB column. We then go and do these insert statements in there. So we basically pass a whole JSON string as a field value. And then later on, we can query that JSONB column and the subfields within that JSONB column. Postgres then takes it, projects it into a column, and displays it to you. You'll also note that we also have an arrow-like operator in there when we're looking for the title, so that you can query semi-structured data in SQL. Since you're extending Postgres, you can also do so much more with this JSONB column. For example, you can count the number of books that have an author defined. You can create a regular B-tree index on one of the subfields in the JSONB column. Or you can create a generalized inverted index, a GIN index, on the entire data. You can then efficiently query your semi-structured data over billions of rows. Postgres will collect statistics about the underlying data and make use of GIN indexes for fast processing. In summary, Postgres can store and process semi-structured data just as well as NoSQL databases. Here on the slides, I have a performance comparison between Mongo and Postgres with the JSONB data type. And Postgres comes with close to 100 data types that each serve many other use cases. And the nice thing is this: if your data has unique properties, you can always extend Postgres and create your own data type. You can even add operators, aggregate functions, and your own indexes, your own index types that are tailored to your data. Next lightning talk. Another workload that almost seems like the antithesis of relational databases is spatial databases. When you think of relational databases, you imagine normalized schemas that serve transactional workloads. In this example diagram, however, that's on the right, we have a map of New York City that captures census data from each census block. This image shows the proportion of different races as a percentage of the total population within New York City. And when you have an online transactional system, how do you even visualize or analyze this type of data in Postgres? In fact, one of the most popular extensions in Postgres does just this. It turns Postgres into a geospatial database. You make Postgres a geospatial database by first creating the Postgres extension. Then, down below, you can create any geometry type, a point, line, polygon, collection, and you can add those types into a table. You can also run hundreds of functions that operate on these geometry types, or you can run location queries. Also, you can use these types, functions, or geospatial indexes as part of your regular SQL commands. In fact, the New York City map that we just looked at in the previous slide was served by none other than Postgres. And you can do so much more with Postgres. This example takes that data and shows the top 10 neighborhoods in New York, ordered by the proportion of people who have grad school degrees. To do this, we're doing a geospatial join between New York City neighborhoods, these 10 neighborhoods, and the census data, where the join operation, that's right there, takes data from the census tract polygons and then joins them with the neighborhood summary data in here. And when issuing this geospatial query, we're both using the aggregate functions that come with Postgres right at the top, and we're also extending the SQL syntax for geospatial joins. In summary, not only can Postgres become a spatial database, but also Postgres is the most popular spatial database if you look at Postgres' Google search traffic versus other databases. And if you need more from your spatial database, you can easily extend Postgres with specific functionality. In fact, after enabling Postgres, you can install 6 additional extensions. These extensions enable topologies, come with algorithms to process 3D objects, or help sanitize postal addresses. So there is no limit to what you can do with your spatial database. Third lightning talk. The next set of questions that we heard about Postgres or relational databases, they were around storage. Can Postgres be tailored to store and query data that's stored in different shapes and form? This question was one of the easier ones to handle. Postgres comes with these new extension APIs called foreign data wrappers that enable it to write to and read from any data source. For example, let's say you keep your data on S3, on AWS. You can then write a foreign data wrapper, and in fact there is one, that knows how to connect to S3, scan over that data, and translate that data into the format that Postgres understands. In fact, these APIs have become so powerful that people use them to query other databases, such as MongoDB, DynamoDB, and even Oracle. In the following slides, I'll talk about CStore FTW. CStore is a columnar store extension that stores your data on a columnar format on disk. As such, it's an interesting example of what you can do with Postgres extensions. Mm-hmm. Mm-hmm.
Plans to add Parquet. And number two, the advantage of column store in terms of most workloads only really becomes evident and becomes powerfully evident when you change the way the executor works.
Yes.
To avoid the back. It occurs that changing the way that the Postgres executor works in this way would require a pretty severe, that's a lot of damage is being done to the Postgres executor. Just those two things. Any thoughts on Parquet and what are the plans for the Postgres executor with respect to the column store code?
Could I think those are very good questions, both of them, and I have answers for both of them too. Yeah. I'll answer them right after that, during the question section. Very valid questions. And then in here, I think when I switch over to this, I'm talking about CStore and then what it does, and then what it's going to do in the future too. So at a higher level, CStore extends Postgres for columnar storage. You can create a columnar table in Postgres similar to regular tables. The only thing that's different is basically you say create foreign table rather than regular create table. And then depending on the foreign data wrapper, CStore is one, but then if it's an S3 foreign data wrapper, you can also specify certain options when you're creating your foreign tables. And as you mentioned, when you create this table behind the covers, CStore will store this data in a columnar layout. For the storage layout, CStore uses the optimized row columnar org format that the Apache Hive project uses. And in this format, in the org format, 150,000 rows are grouped together. And each column data in the set of 150,000 is then grouped together and laid out on disk together sequentially. There is one difference between the org and the CStore file formats. CStore uses PostgreSQL data types as binary representations when storing data. This way, all Postgres data types become immediately compatible with CStore. And you can run your typical Postgres commands to ingest data. Here I'm using copy. CStore will store this data in columnar layout. You can then run your analytical queries right here and then gather insights out of this data. And the nice thing is, by speaking to the Postgres APIs, you can also leverage existing Postgres features. For example, we ran analyze there. When we run this command, Postgres will start collecting statistics about the underlying data, and we'll use those statistics to optimize queries. In summary, it's true that the default storage engine for relational databases has long been row stores. However, this doesn't mean that it's the only thing Postgres can do. In fact, Postgres already has over 100 foreign data wrappers, 104, I counted before I came here, for different workloads. And if you need more, Postgres comes with APIs to scan and update foreign tables, lock rows, or even override the query planning and execution logic. Last and fourth lightning talk. By far the most common objections we heard about relational databases when we started working was around scale. The last decade has been about capturing more data in different shapes and form. And this led to the Hadoop movement and NoSQL databases. And it was these technologies that could help with a data scaling problem. In fact, I heard from many developers the statement, SQL doesn't scale. When we dive deeper into that statement, though, we found that people actually made that statement in the context of very different workloads. And because Postgres could handle all of these workloads, people expected it to scale out as well for all of these workloads. And by this point in the talk, I hopefully started convincing you about the answer. PostgreSQL extensions. Citus is a distributed database that horizontally scales Postgres across commodity machines. To do this, Citus shards and replicates data behind the covers. When a query comes into the database, Citus's query engine routes and parallelizes SQL queries across the machines in the cluster. Citus is packaged as a Postgres extension, and it's available as open source, as enterprise software, and as a fully managed database service on AWS. And you use Citus just like any other Postgres extension. First, at the top, you create the extension. Then, on the tables you'd like to shard, you simply call create distributed table. When you call this function, Citus will create shards for your table. From that point on, any command and query you run on this table, including transactions and sub-transactions, will be distributed. You can plug in your favorite Postgres tool and continue operating as if you were just talking to Postgres. To help visualize things, here's a simplified architectural diagram of Citus. Here I have a coordinator node and worker nodes, and on each one of them is Postgres with the Citus extension loaded. As a user, you interact with the coordinator node. This is where you create your distributed tables. When you create a distributed table, Citus creates shards on the worker nodes, and each shard itself is actually a PostgreSQL table. When you run a query against the cluster, you talk to the coordinator with your standard Postgres libraries and tools. The coordinator then takes that query, transforms that query into smaller queries, and pushes them to the worker nodes in the cluster. Once all the work is complete, the coordinator merges the results and gives them back to the application. In short, the Citus cluster appears just like a regular Postgres instance to your application. Behind the covers, Citus distributes your queries and your data and will scale out Postgres to give you higher performance. When we started working on Citus, the database of choice among developers was really NoSQL. So when we said Postgres, extending Postgres, we'd often be dismissed as SQL doesn't scale. And it's very easy to dismiss a seemingly intractable problem by making a statement that trivializes the problem. And the best way to solve a complex problem is not by dismissing the problem, but by breaking it up into smaller problems and solving them one by one. Because scaling out many workloads is actually solving many small problems. At Citus, the Postgres extension APIs enabled us to do just that. Here I included a few example customers who scaled out their relational databases by simply creating the Citus extension. And over the years, we found that scaling out SQL is a very, very hard, but not an impossible problem to solve. And this brings us to the end of our talk. In summary, Postgres extension APIs offer a unique way to build new specialized databases. In this talk, we went over 4 different workloads that we heard over the years as something relational databases aren't designed to handle. We then showed 4 example extensions that are designed just for these workloads. These extensions are used by thousands of companies around the world. More importantly, you can use these extensions by themselves, or you can use them in combination. In fact, there is nothing stopping you from using the JSON-B extension for semi-structured data, Postgres for geospatial queries, CStore for compression, and Citus to scale out all of them together. To conclude, Postgres 10 enables you to extend any database module. And PostgreSQL's extensible architecture puts it in a unique place for adapting to evolving business and hardware trends. We believe the extension APIs and the extension architecture is a game changer for the database market. It could just be that the monolithic relational database is dying. If so, long live Postgres. Thank you.
Okay, Paul's kind of jumped the gun a little bit here, but
I'm loud and obnoxious.
so yeah.
Okay, and use the mic. Which mic? Oh, that mic. Right, so CStore, the MIT project, and exactly. So Parquet, the more popular columnar organization these days is Parquet, Apache Arrow, Apache Parquet, number 1. Any plans to support that or what's happening there? Number 2, column store databases only really begin to sort of shine dramatically when you change the way the executor works. This is sort of the absolute guts of the expression manager and things like that to make it vectorized. That's going to put do significant violence to the Postgres executor. I was wondering what your thoughts are on that as well.
And on these two, I think they're both very valid questions and good questions. On CStore, we've been meaning to release a 2.0 for a while. We haven't focused on it so much because we've been focusing on the side-to-side side of things. On Parquet, as of now, we don't have any immediate plans, because it's we are going to have to change the file storage format at some point, but that will be backwards incompatible. So we've been debating how to make that backwards compatible, and we haven't reached a consensus on that one. So as of now, we know we need to change we want to change the underlying storage format for other reasons too, like to plug into Postgres' write-ahead logs. But we don't have a specific plan in terms of this is what we're going to change it to. That's the answer to that question. On the execution part, executor part, that's very true. Right now, people who use CStore use it primarily to get the benefits of compression. In order to get high performance benefits, we do need to change the parts of the planner and also the executor. In fact, there is a toy, let's say an alpha version of a vectorized executor that plugs in and takes over from the PostgreSQL executor. But it doesn't offer the full functionality that you would expect from Postgres. I think it's, if you search vectorized_executor, I'll find it for you. You'll see the prototype work that's been done on it. But I think we are thinking of looking at CStore as a project that we prioritize together and go at it. We have a prototype, but we haven't yet taken that prototype to the next stage. I would expect it to come after the file format, because the immediate benefit is more of compression for CStore users.
Other questions?
Okay, I have a question. So the sharding looks quite interesting, but my question is about the replication. How do you approach this problem? They say if you lose one of the shards or partitions, what happens?
Our customers, and I'll go back to that slide, essentially use sharding our application together in one of two ways. One way is Postgres comes with replication. So for each box that you see on this cluster, you can set up a streaming replica. And then when one of the nodes fails, you fail over to the replica. That's the most native Postgres integration because we delegate basically almost everything over to Postgres. A second way, which Citus also enables, is statement-based replication. You can increase the replication factor. And then when you're doing a write, each shard is going to get replicated to not one machine, but to multiple machines. That does have certain caveats, particularly if you have foreign key constraints in between your relational tables. So by default, without knowing more about your workload, we recommend that you use streaming replication for replication and high availability, but it does depend on your workload too.
I see. Okay, thank you.
So I have a question about the JSON support that you have as an extension. So what happens, can you actually deposit different types of data into the same JSON field? Or is it like a very strictly typed system? Like in your example, you have a JSON data where you have things like, say, geospatial index or integers and stuff like that. So does Postgres do any validation when you actually insert the data about their types?
It does validation. And people do this in many different forms. We've seen tables where you have, say, 100 columns with different types and then, say, 5 different JSONB fields. When you write to it, the JSONB type itself, and I think also the JSON type, will validate that what you're putting into it is valid and that it can understand it and then it can index it. And the most typical way we've seen people use this is they have some data, they don't know exactly what's in that data or how valuable that data is. So they just put it into a JSONB column. And over time, they see their customers or their users analyze that, like certain subfields within that JSONB column. What they do is they promote those typical fields into a full-blown column type. So say author in here would become, or a title over time would becomes like they change the schema and it becomes a separate type.
I imagine that you're validating the syntactic validity of the JSON itself, but not applying like a JSON schema to the contents of the JSON field, right? So,
Could you say that part?
so you would not be you'd be validating the quotes balance, that the braces balance, brackets and commas, et cetera, are all correct, but you wouldn't be validating the title is always a string and not a number. Or
Yes,
something like that.
yes. I think in whatever is valid in JSON format, I think it would be validated, and whatever is not validated as part of JSON or JSONB validation would not be validated.
So that's
Okay.
it's still schema at query time.
Yeah.
Okay. I had one quick, maybe philosophical question. If every part of Postgres is malleable and changeable and can be something else, what is Postgres? What is the core? What makes it valuable?
It's the first time I'm hearing this question, and it's a good question. I think there is some core functionality in there, but you can really pretty much extend any part of it. I would say it's what 80% of the users are using, like the components that 80% of the users are relying on, one way or the other. I think that would make up what's Postgres. I think part of it is the parsing part, which I haven't spoken to. That will be my answer. And to be honest, I don't know what that 80% is, what those modules are.
Okay, thank you very much.